everybody, welcome back to Measure Theoretic Probability. In the last video, I said that in this video, we'd be talking about tail sigma fields, or equivalently, tail sigma algebras, and Kolmogorov's 0-1 law. But when I started to think about what we had to say on those topics, I realized that something is coming up that may appear to be a contradiction, but it's not. And I want to spend this video talking about that, and then I'll get back to the tail sigma fields and Kolmogorov's 0-1 law for the next video. So we had a theorem, I think 2 lessons ago, lesson 10, I think, that if we had independent collections of sets, curly A1, curly A2, etc., and if they were pi systems, then the sigma fields generated by curly A1 and the sigma field generated by curly A2, etc., are independent collections. And we saw an example of this result going from independent classes to sigma fields generated by independent classes not being independent when we didn't have a pi system. Let me remind you of that example. We flipped a fair coin twice. You can get heads, 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 tails, tails, heads, or tails, tails. And we defined 2 classes of sets. So I'm going to define them here again, although I'm using different notation from the last time we did this example. I'm going to let curly A1 be the collection consisting of one set, and that set is the set of 2 outcomes, heads, tails, and tails, tails, and I'm going to call that single set A1. I'm going to let curly A2 be a collection of 2 sets, each with 2 elements. I'm going to call them A2 and A3, and A2 is going to be heads, heads, tails, tails. A3 is going to be heads, 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 tails. Now, it's easy to show using regular probabilities involving flipping a coin twice that the probability of A1 intersect A2 is the product of the individual probabilities, and so is the probability of A1 intersect A3, and that's what we need to show these 2 classes are independent. Take any one thing out of this and any one thing out of this. Look at the probability of the intersection. We need it to factor, and that tells us the classes are independent. In this example, we actually have some bonus independence. It turns out that these 2 sets are also independent, which is not necessary to be looking at 2 independent classes. So we saw that the sigma field generated by curly A1 is not independent of the sigma field generated by curly A2. And we showed that by actually finding a common element in both sigma fields. So if you have a set A that's independent of itself, that means that the probability of A intersect A needs to be the probability of A times the probability of A, which boils down to the probability of A being the probability of A all squared. This can happen if the probability of A is 0 or 1, and we do have that when A is the empty set and omega, but we can also have 0 or 1 probabilities, even if A is not the empty set or omega. However, the specific set we found had probability 1/2, and 1/2 is not equal to 1/2 squared, and so that's how we showed that this held. In other words, independent classes does not necessarily imply independent generated sigma fields. So we had this theorem I just recapped saying that if you make these curly A's pi systems, that's enough to guarantee the sigma fields are independent. And we had this example saying that if they were not pi systems, we can't guarantee that they're independent. Here's something new, which is going to look similar to that second result, that counterexample. And you may think I'm contradicting myself. Maybe not. So I'm going to start out small with 3 independent events or sets. A1, A2, A3. These are not curly A's. These are not collections. And I claim that the sigma field generated by A1 and the sigma field generated by A2 and the sigma field generated by A3 are independent. Now, this should not be surprising for 2 reasons. Number 1, we know that if A1 is independent of A2, then the complements are independent, things like that. And these sigma fields each contain 4 elements. The sigma field, for example, for A1 contains the empty set, A1, A1 complement, and omega. A2 contains the empty set, A2, A2 complement, and the omega, etc. So if we started with independent sets, it's easy to see that these classes are still independent, because if you take anything from any one of the sets and anything from any other one and look at the probability of the intersection, it does factor to the product of the probabilities, including 3-way intersections. The second reason this is maybe not surprising is because this is covered under the theorem that I recapped at the beginning today. Because if I'm just looking at generating with a single set, A1, A2, and A3, you can think of these as collections curly A1, curly A2, and curly A3, where each collection contains only one set. And if each collection contains only one set, then it is a pi system, because just having the set A1, for example, that's closed under intersections. A1 intersect A1 is still A1, and it's still in that collection. So there are two reasons right there that you should not be surprised by this claim. Okay, so a second claim, which might surprise you, is that the sigma field generated by A1 is independent of the sigma field generated by A2 and A3. So this little collection of sets in here is not a pi system, unless maybe A2 is contained in A3, but in general, the intersection of A2 and A3 is not one of A2 and A3. So not a pi system. So is this surprising? This right here looks like our coin example, where I have a collection curly A1 consisting of the single set A1, and a collection curly A2 consisting of A2 and A3. And the sigma fields generated by curly A1 and curly A2 were not independent in that coin example, but they are here. Is this a contradiction? Before I answer that, let me give you one more independence result here. I can also say that the set A1 alone is independent of the sigma field generated by A2 and A3. And that's actually contained in this result here, because A1 is in the sigma field. I write this one down because this is a particular result that we're going to need in the next video. So now, is there a contradiction here? I appeared to have independent sigma fields, starting with independent collections of sets, and they were not pi systems. And we saw that coin example where this did not have to hold. The answer is no, it's not a contradiction. And the reason is because in the coin example, we had three sets, A1, A2, A3. A1 was independent of A2, A1 was independent of A3, and we had that bonus independence with A2 and A3. And this is enough to say curly A1 is independent of curly A2, because for those to be independent, you need to take any one set in here and any one set in here, look at the probability of the intersection, and see that it factors. That's not what I said on the previous slide where I'm making this new claim about independence. I said that A1, A2, and A3, those three sets, are independent, and that means that they're mutually independent, not just pairwise independence. In our coin example with the specific sets, A1, A2, and A3, we could show using coin probabilities that, well, A1 intersect A2 intersect A3, there's actually nothing in common there. That's the empty set. So the probability of that three-way intersection is 0. Whereas the probability of each of those sets with two elements is each 1/2, and 0 does not equal 1/2 cubed. So we did not have mutual independence between the three sets, A1, A2, and A3. So that's why claiming this new result, starting with all independent sets and maybe grouping them into collections, and then making sigma fields out of those without them having to be pi systems, is not contradicting that example. Because in this claim, I am assuming more independence than we had in the coin example, mutual independence. So let's kick this up a notch. Suppose that I have a whole bunch of independent events. I'm going to organize them in an array, A11, A12, A13, A21, A22, etc. And suppose they are all mutually independent. I'm going to let curly f sub I be the sigma field generated by the ith row. So you can think of this as a collection curly A1, and this is a collection curly A2, etc. Then I'm just looking at the sigma fields generated by the different collections, starting with every one of the individual sets being independent, not just pairwise independent. I claim that these sigma fields are going to be independent. We're going to sort of show this today. I'm going to show a slightly watered down version of this, and the proof is really not very different at all. I just thought it would make for a cleaner proof for the video, a little, just slightly less tedious. So what are we going to actually prove today? I'm going to call this new theorem 2, and I'm going to suppose that A1, A2, A3, etc. is a list of independent, meaning mutually independent events, so not the whole array. And I want to show that the A1 set is independent of the sigma field generated by all the rest of the sets. I can do many things here. I could show that the sigma field generated by A1, A2, A3 is independent of the sigma field generated by A4 and A5. We can do all sorts of things, but I need this particular result for proving Kolmogorov's 0-1 law. To prove it, I need to prove something else ahead of time. So I have a theorem for you, and it says that If you have two measures, probability measures or otherwise, agreeing on a pi system, so you have some space like an omega and an f, and then you have a pi system, curly p, which is a collection of subsets of omega that's closed under finite intersections. And I have two measures, which could be probability measures or even not. So let's say mu1 and mu2. If they agree on sets in the pi system, then they're going to agree on the sigma field generated by that pi system. I'm going to prove this, but first let me make that even more concrete. Let me set up some notation. We saw, by the way, something like this back when we were talking about outer measures a long time ago. And at the end of that video, I actually set a result that was kind of like this that I didn't prove. And instead of having pi systems, I had fields, but having pi systems is a weaker assumption. So if we prove this, we will have proven that unproven result at the end of the P star outer measure stuff. Here is my notation. Suppose I have a non-empty set omega. I have a pi system curly p of subsets of omega. I have a sigma field curly f defined to be the sigma field generated by curly p. Suppose I have two measures, mu1 and mu2, that have a couple of properties. Number one, they need to be finite, and this is certainly satisfied for probability measures. Again, we're doing this a little more generally. And number two, they have to have the same value when you evaluate the full omega. So mu1 of omega has to be mu2 of omega. Now, if we had two probability measures, they both have to evaluate to 1 when you plug in omega. So that's something that's also automatically satisfied by a probability measure. So if the measures agree on P, meaning if you take a set A out of the pi system, if mu1 of A is equal to mu2 of A for any A you pull out of the pi system, then I claim they agree on the generated sigma field. So you can take an A out of the sigma field generated by the pi system, and mu1 of A has to equal mu2 of A. That's what I want to prove in this theorem, and then we can go back to the theorem for today, which talks about independence of an event and a sigma field generated by other events. Let's prove this one. First, I just want to remind you, so you have it in front of you, curly f is the sigma field generated by curly p, which is a pi system. I'm going to define a new collection of sets. I'm going to call it curly A. This is going to consist of all sets A from the sigma field, for which we do have equality of the measures when you evaluate both at A. Clearly, this is a subset of F because of this part right here. I'm going to look at all sets in F such that, and that's going to narrow it down to maybe not be all of F, but curly A is going to be a subset of F. If we want to show that mu1 of A equals mu2 of A for all A in curly F, then we just need to show that the collection of sets for which mu1 of A is equal to mu2 of A is all of curly F. In other words, we've got that curly A is contained in curly F. We're going to show containment the other way. So first off, I'd like you to note that the pi system curly P is contained in curly A. We know that curly P is contained in curly A because that was the assumption, the setup here. We assumed that mu1 of A is equal to mu2 of A for everything A in that pi system. I claim that curly A is a lambda system. We're going to show that. It's not too difficult. Once we show that, we can finish off the proof. I'm going to finish it off right now and then come back to showing it's a lambda system. We're going to use Dinkin's pi-lambda theorem. I've got a pi system curly P. I've got a lambda system once we show it, curly A. P is contained in curly A. And by Dinkin's pi-lambda theorem, the sigma field generated by curly P, which is known as F, must be contained in the lambda system curly A as well. And this containment is what we wanted to get our final result. So we're done with this proof. Once we have shown that curly A is a lambda system, let's do it. We have 3 things to show. I'll just remind you that curly A consists of the sets for which mu1 is equal to mu2. And we've got I. I, for the definition of a lambda system, we want to show that this set contains omega. And this is by the setup of the problem. We did assume that mu1 of omega is equal to mu2 of omega, and that means that omega is in curly A. So check for that one. We want to show it's closed under complements. So I'm going to take an A in curly A. Now this means that mu1 of A is equal to mu2 of A, And we want to show that mu1 of A complement is equal to mu2 of A complement. So let's start with mu1 of A complement. I can write it as mu1 of the full omega minus mu1 of A. Why can I do this? This is kind of like the complement thing for probability measures. I'm just using countable additivity. We know that A and A complement are disjoint and their union is the full omega. So by finite additivity, which is a special case of countable additivity for the measure mu1, we know that mu1 of A plus mu1 of A complement is equal to mu1 of omega. So here it's just unraveled. Now we did assume that mu1 of omega was the same thing as mu2 of omega. And because I'm starting with an A from this set curly A, we also know that mu1 of A is equal to mu2 of A because that's how we define inclusion in A. So I can rewrite this line and change the mu1s out for mu2, and then I can use countable additivity the other way around. This is mu2 of A complement. So we've shown that mu1 and mu2 agree when you plug in A complement. Therefore, A complement must be contained in this curly A. And that is part 2 of showing it's a lambda system. So part 3, or triple I, we want to show that it's closed under countable disjoint unions. So let's take a countable collection of disjoint sets, A1, A2, A3, etc. from curly A, and let's look at mu1 of the union. If we can show this is mu2 of the union, then we have shown that that union is in the curly A, and we are done showing this is a lambda system, and therefore done with the whole proof. So, so let's do it. Mu1 of the union, because mu1 is a valid measure, and because this is a union of disjoint sets, I can use the countable additivity property of a measure. I can rewrite this as the sum of mu1 of the individual A's. But because these A's came out of curly A, mu1 of each of these A's is the same thing as mu2 of each of these A's. Now I can use countable additivity in reverse to bring that sum back in, and we have shown that mu1 of the countable union of these disjoint sets is the same as mu2 of the countable union of the disjoint sets, and that means that the union of these disjoint sets is in A, and that's the end of showing that A is a lambda system. So then we can apply Dinkin's pi-lambda theorem, and we're done proving that if you have a pi system and you generate a sigma field, if you have two measures that agree on sets in the pi system, they will agree for all sets in the sigma field. Okay, so the last thing for today is to prove our new theorem, or new theorem 2, which is where I watered it down just a little bit, but in a way that we're actually going to need. So take some independent events, A1, A2, A3. These are single events, not curly A's, not collections. And I claim that A1 is independent of the sigma field generated by the rest of the A's. We are dealing with an infinite number of sets here and independence, and recall that independence, when you have an infinite number of things, is defined through independence of all finite subcollections. So let's take an integer n greater than or equal to 2, so we'll consider a finite subcollection, and I'm going to define curly A to be the collection of sets of this form. A2i, which I'm going to define in a second, intersected with A3i, out through intersected with ANI. Now, A2i, for example, can only be one of four things. It can be this A2 up here, it can be the complement, it could be the empty set, or omega. Similarly, A3i could be this A3 up here, it could be its complement, it could be the empty set, or omega. And we keep going like that. So curly A was defined using some finite intersections, and by definition, it contains or is closed under finite intersections. So curly A is a pi system. Furthermore, the sigma field generated by curly A is the same as the sigma field generated by A2, A3, A4 on up. Why is that? Because I can form this kind of set using these guys, and I can get these guys from this kind of set by taking several of these to be omega. For example, if A2i is chosen to be A2 and all the rest are omega, I can get the individual A2 back. Similarly, I can get the individual A3 back. So we can get back to the base components for building this sigma field, and we can get the base components for this sigma field out of these. So these are going to give us completely equivalent sigma fields. Note that for a set A in curly A, we have that the probability measure of A intersected A1 is the product of the individual probabilities. You'll recall A1 is that first independent set. We had A1, A2, A3, and we sort of put A1 aside and are looking at the rest of them and generating a sigma field. So because A1 is independent of A2, A3, A4, and therefore also the complements, and really if you just look at this, if you form this as an intersection of n things, it's easy to show using independence of the original A1, A2, A3 that you're going to get this factorization. Now, if I solve for P of A, I get the probability measure of A represented in this way. And this is true for all A in curly A. I'm going to define a probability measure. I'm going to call it P tilde on the sigma field of interest, the sigma field generated by A2, A3, A4 on up. And I'm going to define it to look just like P. So P tilde of A for any A in this sigma field is going to be defined to be P of A intersect A1 over P of A1, where P is the original probability measure. So you might want to take a moment to verify that P tilde is in fact a probability measure on this space. It really inherits all the properties it needs from this probability measure. It needs three things to happen. We need P tilde of the empty set to be 0. We need it to satisfy countable additivity. And we need P tilde of the full omega to be 1. Let's look at that one real quick. P tilde of the full omega is P of omega intersected with A1 over P of A1. But omega intersected with A1 is A1. So P of A1 over P of A1 is 1. So we're good to go with at least that property. And the others are just as easy. So I define a new probability measure, P star, on the sigma field generated by A2, A3, A4 on up. And by design, it agrees with the original probability measure when you're plugging in sets from curly A. And curly A is a pi system. So here's where I want to use the theorem we proved just before going into this theorem. I've got two probability measures that agree on a pi system, so they're going to agree on the sigma field generated by the pi system, which we already mentioned is the sigma field generated by A2, A3, A4 on up. So what does this mean? If I take an A in this sigma field, P of A is equal to P tilde of A by our previous theorem. But P tilde of A was defined like this. So even though we had this result, this equals this on curly A, we now have this equals this on the sigma field generated by curly A. Equivalently, we're saying here for any A in this sigma field, the probability measure of A intersect A1 is the product of the individual probability measures. So that means that for any A in the sigma field, it is independent of A1. And that's what we wanted to show. We wanted to show that the set A1, which you can think of as a set of one set, is independent of the whole collection, sigma, generated by A2, A3, A4 on up. That's what we wanted to show. Now we're done. In the next video, we're going to talk about tail sigma fields, or sigma algebras, and these are sigma fields generated by the tails of sequences. So we're going to have events A1, A2, A3 on up. A tail sigma field is going to be a sigma field that can be described using part of the sequence where you can cut off any finite number of those terms. And we need to define this in order to talk about Kolmogorov 0-1 law, which is kind of like a generalization of the Borel-Cantelli lemmas. They're going to give us conditions under which certain events have probability measures 0 or 1. And the use of that is going to be for the next video, where we're finally going to talk about random variables. So I hope to see you there.